Now I want to relate the Fourier series to differential equations. So think about the following question. Let's say you have an endpoint value problem with, let's say you have an endpoint value problem. Say you have y double prime plus 4y equals to, let's say, t. And you have y of 0 equal to y of 2 equal to 0. So you can think of it like this. Your function, whatever that function is, if you drew the graph of y of t with t, then at the endpoints at 0 to 2, it has to be this. It has to be 0 at the ends. I don't know what happens in the middle. I have no idea how the thing looks like, but whatever it does, it has to be 0 at the endpoints. And between 0 and 2, between the t values 0 and 2, we want to say this is satisfying. So we want to find the continuous function where at the endpoints it's fixed to 0, and inside you have this satisfied. Okay? Usually you apply this method for the case when this right side, the non-homogeneous term, is a function that's not continuous. And the reason for that is if it's like just like t, then you can just use your old method. What's the old method for dealing with such a thing? Method of what? Undetermined coefficients, right? So you can find a particular solution, find a complementary solution, add them up to find the generic solution, and then you apply the endpoints, and then you can find the solution. Okay, so that's certainly one way to solve this. And if you see how Fourier series is used to solve this one, it's much more overwhelming than you might say, oh, that this method is useless. Well, but in reality, the method that I'm about to explain to you is valuable, especially when the function on the right side is a piecewise function. Because if it's a piecewise function, you can still find the Fourier series, right? We can find Fourier series of piecewise function. And you can solve it using this method. Whereas methods of undetermined coefficients only work for very narrow case of the right side, right? If this is like exponential, sine, cosine, or polynomials, or mixture of those, that's the only time when you can use method of undetermined coefficients, right? All the other cases, I told you that you'll be forced to use what's the other one? Variation parameters, right? But if it's not even piecewise, if it's not even a continuous function, if it's piecewise, then even that method variation parameters would yield integrals which is hard to compute, right? So at a certain point, you will see that the only way to go about solving these type of questions is by Fourier series when the right side is extremely nasty. Okay? But I just want to show you this method using t. I chose something simple just because I don't want the calculation to be too daunting. Okay, so I'll just try to solve this. And maybe after this solution, you might see what the general method of the approach is. Okay? All right, so solution. Now here's my plan. You see, among sine and cosines, which one satisfies the property that at these endpoints it's 0? The sines. Because sine of 0 is 0, whereas cosine 0 is 1, right? So there are actually two types of problems in this type. You are sometimes given that the value is 0. In that case, you choose sine. The value, when the value is 0, you choose sine. You use the cosine when the derivative is 0. Okay? So those are the two flavors. When you have these endpoint value problems with Fourier series, there are two kinds of questions. One where the value is set to 0, another where the derivative is set to 0. If the derivative is set to 0, you use cosine. If the value is set to 0, you use sine. So here's what I want. I want to think about the function y as Fourier sine series of something. Makes sense, right? I can just think about y as sum of sines. Okay. Now what's the value of L here? Because it's from 0 to 2, right? It's from 0 to 2, your L should be 2. From n from 1 through infinity. So this is the ansatz for the solution. Okay? We're predicting that I can find a solution that looks like this that satisfies this. Now, because I wrote the generic form for this function y, we will get the solution if we find all the Cn's, right? So once I write it like this, now our goal is to find Cn. We want to find certain Cn's so that when I plug this entire thing on the left side, it matches with the right side. That's what I want to do. All clear so far? Okay. All right, so let's plug this into the left side. To plug into the left side, you have to differentiate this twice because it's double prime, right? So we differentiate it twice. Well, every time we differentiate, this comes out, right? And the sine, derivative of sine is cosine, derivative of cosine is negative sine. So you're going to end up with negative n squared pi squared over 4 Cn times sine n pi over 2x. Okay, so all I did was I took this function and differentiated it twice. Why did I do that? Because I want to plug this on the left side. Okay? So I plug this on the left side. Let's see what we get then. Y double prime plus 4 times y is sigma n from n1 to infinity of negative n squared pi squared over 4 Cn sine n pi over 2x plus 4 times sigma n from 1 through infinity of Cn sine n pi over 2x. I messed up, sorry. There's an important thing important error that I made. All the x's here should be replaced by t. Why?
Because you solved the t.
Because the right side is t. It indicates that y is a function of t, not of x. I should have written it as t. Sorry about that. Okay, now I have these two added up, which is sigma n from 1 through infinity. See, Cn sine of n pi over 2, that's common. So I can just put that aside. I can factor that out. If I factor that out, what's left is, for the first one, I have negative n squared pi squared over 4. And from the second one, 4 goes inside, and 4 is left if I factor this out. So that's what we get. So that's what you get if you computed the left side with using this ansatz. Okay. Oh, and another thing I want to say is that look at this. What is y of 0? Y evaluated as 0. If you plug in t equal to 0, what do you get? Sine of 0, that's 0. Right? So it satisfies this y0 equal to 0, right? What do you get if you evaluate this at 2? If you plug in t equals to 2, what do you get? Sine of n pi. What's that? 0. So it satisfies this other one too. So if you set your y in terms of this ansatz, I mean, certainly any function has its sine series, right? So I'm representing it as its sine series. But the nice thing about representing the function as a sine series is that the endpoint value condition is met automatically. So that we don't have to worry about. So that's met, and we computed that. And now the only thing that we need to verify is that I want that thing to be equal to t. Okay? And specifically, I'm looking for the Cn values, which will make this entire sum equal to t. Yes?
When you're taking derivatives, why didn't you change add on the bottom like the n equals 3, like we did with the series? Like
Oh, this one, in this power series solution, when you differentiate, certain terms became 0 when you differentiate. In the power series, when you have the constant terms become 0. That's why we had to modify where n began.
No, I meant like, why wouldn't it be like n equals to 3 for y double prime? Because like y prime, I thought would be like n equals
Yeah, so that's what I'm saying. Here, n equals to 1 because the first two terms don't disappear when you differentiate.
Oh, okay.
See, you're talking about this power series solution when we had n equals to 0 to infinity of an x to the n, right?
Mm-hmm.
See, the very first term when n is equal to 0, you get a0 x to the 0th power, which is a0 by itself, which is a constant term.
Yeah.
When you differentiate it, what happens to a0?
It goes to 0.
It goes away, it becomes
Yeah.
0, right? So when you differentiate, you're no longer going to see a0 at all. So what do? You modify it to begin at n equals to 1. But that doesn't happen here because none of these functions become 0.
Okay.
Okay, that's the difference.
Thank you.
Good question. Yeah. All right, so back to this. So what should we do? What's our strategy? How do you match this with this to figure out what Cn should be? What should we do? No idea?
Integrate.
Well, no, we take the sine series of t. We want to represent t as bn sine n pi over 2t. That's the goal. So how do we find bn? The formula is 2 over 2, 0 to 2 of t sine n pi over 2t dt. Okay, I doubled it because this is an even function. So instead of integrating from -2 to 2, I'm integrating from 0 to 2. So if I compute this, this is going to give us the t in terms of something times sine n pi over 2t. And now if I equate this with that, I see that whatever I get here has to equal to this times Cn. Then solving for Cn, we get the final answer, right? So let's do this quickly. The tabular. Not working. Plus minus d integral t 1 0 sine n pi over 2t negative 2 over n pi cosine n pi over 2t negative 4 over n squared pi squared sine n pi over 2t plus minus plus, and that gives you the integral. Negative 2 over n pi t cosine n pi over 2t, and then plus 4 over n squared pi squared sine n pi over 2t, and then you're plugging in 2 and 0. When you plug in 2, you get negative 4 over n pi negative 1 to the nth power, and when you plug in 2 here, you get sine n pi, which is 0. When you plug in 0, 0 times anything is 0, sine of 0 is 0, so this is the only thing that you get. And therefore, plugging this back in here, you get your t equal to sigma of n from 1 through infinity of negative 4 over n pi, negative 1 to the nth power, times sine n pi over 2t. And then if you compare this with that, now we see what the equation must hold. The equation that must hold is negative n squared pi squared over 4 plus 4 times Cn has to equal to b, this coefficient here, negative 4 over n pi, negative 1 to the nth power. So now you divide this over, you have to divide this entire thing. And this complicated thing is your Cn. So here's the final answer, which is very complicated, but it is an answer nonetheless. So all these answers come out really nasty, but it's still usable. Okay, so y is equal to, that's the answer. The answer is y equal to n from 1 through infinity of negative 4 over n pi, negative 1 to the nth power over negative n squared pi squared over 4 plus 4 times sine n pi over 2t. Okay? So that's how you solve a Fourier series, solve an endpoint value problem using the Fourier series. And the significance is, although this is actually quite stupid given that this is the question, right? But it's more useful when your question is given as piecewise function on the right side.